Welcome to the Math Help channel. Today's video we will cover integration and a tool that will aid the process of integration, and that is u-substitution. I'll go through a few examples, one relatively easy and then a couple that are slightly more difficult, just so you can see how the process works. I'll explain what the process is, and then, like I said, then I'll go through a few examples. Okay. First example. All right. So, for example, I'm gonna assume you guys know, what antiderivatives are and things like that. So I'm just gonna go ahead and go right through it. All right. So let's say I start with, let's see, x times x squared plus 1. Let's make that squared. Okay. So let's say I want to integrate this function. The idea here is the u-substitution is essentially the chain rule backwards. And remember the chain rule, and recall the chain rule. Whoops. Chain rule for derivatives is f of g of x, its derivative equals f prime of g of x times g prime. Okay, remember that? So essentially we are going from here and we want to arrive at this. Okay? So that means what we're going to do is we're going to assign the inner function a variable. The first step is to assign the inter variable a function. Alright, the inner function a variable. So generally, since it's called u-substitution, we're going to make this u. So we're going to say this is, so let u equal x squared plus 1. Now, since this is the outer function, we don't really care what happens to this. This is okay. We only care what happens to this, because when we take the derivative of this, remember, it's what comes out. And notice that the exterior function, or we have that exterior function, notice that its derivative, this g prime right here, sort of needs to match this. So that means the derivative of this must match or have a common factor to this, which means a constant term, no variables. So if there's if I essentially said, this was x cubed, and I took its derivative, this would be 3x squared, and that doesn't match or have a common factor with just x, a constant common factor. Moving on, so what we'll do here is we're going to take its derivative, and we're going to do it implicitly. So implicit differentiation, we get du equals 2x dx. Okay, and this is where the u-substitution begins. So what we want is this side to match this side to match this over here. Now what I can do is to match these together. So the way we're going to do that is I can rewrite this integral as x squared plus 1 squared times x dx. Okay? I want this to look like this. The only way I'm going to do that is, I want this to look like this. The only way I can do that is divide both these expressions by 2. So we're going to divide everything by 2, and so we get du over 2, or let's make it a little bit simpler. 1/2 du equals x dx. Okay, so now we have this substitution, and we have this substitution. Because of this, because we wrote this expression in terms of u and this expression in terms of du, we can now make that substitution. So if you take a note that, so basically u substitution, this is u, and this should be du, or not the whole thing, just the inside. Okay? So now that we have that, we can now plug, so now we can replace this with u and this with that. So now we get, so now we have, it goes from x squared plus 1 squared times x dx. We can now make the substitution. We get the integral of u, remember, u squared, because we make that substitution, times, and du is now going to be 1/2, or dx, the x dx is now going to be 1/2 du. Much simpler function. If you remember your basic rules of integration, we can bring this 1/2 out front, because it's just a constant, a coefficient. So we get 1/2 integral of u squared du, and that is a much more, an easier function to integrate. So then we just integrate that. If you remember, you increase the power by this power by 1 over the new exponent. And remember, since this is indefinite, which means there are no limits, we have to put a plus c at the end. If you remember why we put a plus c, is because the derivative, if you work backwards, remember work backwards of finding the derivative of a constant is 0. So we multiply that out, we get 1 over 6 u cubed plus c. But remember, that's not quite the answer. Remember, the problem is in terms of x, not u. So what we'll do is, remember what we substituted in for u? Or what we substituted in for x, the original x plus 1 was u. So let's put it back. So that means we get 1 over 6 x squared plus 1 cubed plus c. And that's your answer. Okay? Let's try one that's a little bit more difficult. Okay, let's try one more. So we get, let me see if I can come up with one. Let's see. Let's try tangent. No, let's not try tangent. I don't like tangent. Sine of sine x times 3 cosine x. Okay, maybe not slightly more difficult. The idea is to get the idea across. So what we're going to do is, now remember, multiplication is commutative, so we can put it in any order we want. So what we can do is, first we can just go ahead and put this 3 out front. So now, if you remember, when we said that the first half was u and the second half is du, I'll put it in general form. This is when you have u substitution. It's u dot u times du. This is u substitution. So we want to make one of these u and one of these du, such that when you take the derivative of u, you get some scalar of this, or a multiple of this. Remember, you can't use any variables. So let's call u, let's make u equal to sine x. You know what? Let's do this. We can't do that. Sine x. Okay? Alright, so remember, now we take the derivative with respect to implicit differentiation. So the derivative of u is du. The derivative of sine x is cosine of x. dx. Right? Remember, we're doing, oops, did not show up, did it? My bad. Okay. Oh, sorry, you guys. That right there might look like a minus sign, but it's an equal sign because I have a glare, apparently. So, du equals cosine of dx, and wouldn't you know it, that looks just like that. So we don't have to make any changes whatsoever. So we just go ahead and substitute u for sine and du for this expression here, because this is what we have. Because fortunately, when we took the derivative of sine x of our original u, we were able to get du dx. So let's make the substitution. So we were at 3 sine x cosine x. And when we make our substitution, we get, remember that this doesn't change. This is just a constant coefficient, so you can just leave it out there. It's not going to affect anything. Answer will stay the same. So then sine x is u, cosine x dx is du. And isn't that an easy function to integrate? So we get 3 integral of u. Remember, you increase the power by 1 and put it over the new exponent, and then plus c. So 3 halves u squared plus c. Now remember that the answer, this is not quite the answer, because our original problem is in terms of x, not u. So that means what we're going to do is we can substitute sine back in for u. And the reason we were able to do that, remember, is because we made a correlation between x and u by finding the derivative. We chose an appropriate u and took its derivative. And when we took its derivative, we were able to get the other product of our integral. So that's why we are able to switch it back. So then that means we get 3 halves sine squared of x plus c. All right. I will do. Let's do one more. One with a square root, because I don't know if many of you calculus students out there have recognized it or not, but radicals will be are pretty evil unless you recall one thing from algebra or advanced algebra trig, how to convert between radicals and exponents. I'll cover that real quick. So you have the a root of x to the b. That's the same thing as x to the b over a. So the b is the exponent in the radical, and a is the power of the root. That make sense? Okay. Moving on. Let's do one more problem with what do you call it? With a radical. So let's see if I can come up with one. Ln of, let's do secant, alright, how about this? Let's do the integral of secant squared x times ln of tangent x dx. Now, yes, I'm using an obscure function, but remember, I mean, that's the idea of calculus, or that's what calculus calculus, you're going to see all kinds of these obscure functions, because the fact that you're in calculus or AP calculus or whatever you're taking, your teacher understands that, or should is comfortable with the fact that you know the basic functions, all of those parent functions and things like that, and all the easy linear combinations and all that. So they're not testing you on whether you can do the easy ones. They're going to see if you can handle the hard ones. So you're going to see a lot more of those. So let's try this again. Now, unless you want to make that, so now we need to choose a u and a du. Unless you want to make that u and take its derivative, do you think you're going to get ln of tangent x? No, I don't think so. So what we're going to do is we can make, let's make this a u. Let's make that a u. Now, we don't have to make the entire function a u. Remember, it's the interior function that needs to be a u. So usually it's an interior function that can be that has to be u. So let's make u equal. So let's rewrite the function as, or the integral as ln of tangent x times secant squared x dx. So let's make u equals tangent of x. Now, I'm going to assume you guys know the derivative of tangent x. I don't think I need to derive that. If you need to derive it, remember you can, to derive, you can just change tangent to sine x over cosine x and use quotient rule. Okay? You can just change tangent to that. So I'm not going to go through that derivation. I'm pretty sure you guys can handle that, okay? If you just change tangent to this and just use the quotient rule. And once you go through all that, the derivative of tangent is secant squared. Now remember, we're taking the derivative of this implicitly. So you take the derivative of both sides. So the derivative of u is just du. The derivative of tangent x is secant squared dx. Unfortunately, again, this is the same as this. There's your du. So now we can make our substitution. So then the integral of ln of tangent of x times secant squared is the same as saying ln of u, and remember this is now du times du. So now we can integrate. We can now integrate with respect to u. And when you integrate ln of x, believe it or not, this is a formula that they will possibly even give you, and this is u ln u minus u. Okay? And then plus c. Okay? This, this can be derived from a method that you will learn if you're in AP Calc BC. You will learn this a little bit later on in the spring semester. This is called integration by parts. If for all you AB students, you won't learn this until you take Calculus 2 in college. Remember, this is not quite the answer. So what we need to do is make we can substitute our expression for u right back in. So this equals tangent x times ln of tan x minus tan x. Now we can factor out the tangent right there, so we can just say tangent x times ln of tan x minus 1. And that's it. If you guys have any more questions, please post comments to this. please subscribe. And if you guys have any more, if you have any problems you'd like me to work, any concepts you want me to cover, please send me a message or comment on any of my videos, and I'll get to it as soon as I can. Thanks for watching. Have a good day.